This is Mihao Cui from University of Massachusetts Amherst, and I'm going to present work RadioInLight, doubling data rate of VLC systems. This work is achieved by great collaboration with Qing Wang from Delft University of Technology and my advisor Jie Xiong from University of Massachusetts Amherst. So in recent years, we have seen the rapid evolution of mobile networks. The 5G has been deployed and the competition for 6G has already started. Visible light communication as a key potential component of 6G has already attracted lots of attention from both academia and the industry. As visible light has a very high frequency compared with the radio frequency signals, it has the potential to become a very high data rate communication technology and meanwhile less interference with the existing communication technology. Recently, research found that while the wireless transmitters is sending out light signals, it also leaks RF signals. The reason why such RF leakage exists is the intensity modulation, well adopted in most of VLC systems. In the intensity modulation, the wireless transmitter will transmitting the data bits 0 and 1 by turning off and on the LED bulb. And I'll give you a simple illustration. So during the VLC transmission, it transmits data 0 and 1 by turning on and off the LED bulb. The current in the power line will change correspondingly. So such rapid current change will induce the electromagnetic signals in the near field according to Maxwell equations. And we call these electromagnetic signals as the leaked RF signals. The existing work utilizes such leaked signals to conduct sniffing attack on VLC systems through the walls. The reason why this attack can work is that the leaked RF signals carry the same information as the visible light channel. So since such RF leakage always exists, we ask this question in our paper: can we transmit additional data through the leaked RF channel? The answer is yes, of course. So we proposed a RadioInLight system that can utilize the leaked RF signals to double the data rate of VLC systems. Although it sounds very great, and we also still need to solve some challenges to make the system work. The first challenge is that how to encode the data using the leaked signals. As we all know, that the leaked RF signal is a byproduct of VLC channel. So they're fully dependent on what is transmitted in the VLC channel. For example, if you want to encode data with the leaked signals, the first method is that we want to control the amplitude of the leaked signals by controlling the amplitude of the VLC signals as the multi-level on-off keying. Or we can change the positions of leaked signals by changing the positions of VLC signals as variable pulse position modulation. Unfortunately, although they can encode the information in the leaked signals, but they all influence the original VLC channel. So we need a modulation scheme which can control the leaked signals without influence on the original VLC channel. Interestingly, we find that the current changing rate in the power line will largely determine the amplitude of leaked signals. And in details, the larger the current changing rates, the larger amplitude of leaked signals. So we propose a novel slope shift keying SSK modulation for leaked signals. It mainly uses the current changing rates to modulate the amplitude of leaked signals. And we find that connecting a resistor between the signal source and MOSFET can form a RC circuit which can slow down the current change in the power line, which will result in much smaller amplitude signals. But here comes another challenge, is that as we all know that the leaked signals are created by the VLC channel. So when the VLC on-off rate is increased, then it means that there are more leaked signals in a fixed time window. In order to fully modulate all the signals to achieve a high data rate, we need to switch the resistors of different values very fast as the VLC on-off rate. The traditional method to switch resistors only uses the potential ohmmeter, and there is also a digital version. However, most of them have too slow switching frequency, and there is an unwanted vapor resistance which will influence the communication range. So we propose to use MOSFETs for achieving a high-speed SSK modulation. The proposed circuit consists of resistors of different values, result in different amplitudes of leaked signals, and MOSFETs that controls which resistors will be connected into the circuit. Since the MOSFET can easily achieve a 60 megahertz switching frequency, so it is fast enough for our design. Now I give a simple example about how our proposed systems and modulations could encode the encode information in the signals. Without any SSK modulation, the GPIO1 will transmit alternative on-off symbols or on-off signals to the MOSFET, and MOSFET will correspondingly changing or turning on-off the LED lights to send signals. The only difference is that we connect a resistor A between the GPIO1 and the MOSFET, which will largely slow down the current change rate, result in a much smaller leaked signal, as shown in the blue symbols here. Then, with SSK modulation, the GPIO1 will still transmit the same alternative on-off symbols, but the other GPIOs that controls MOSFETs for different resistors will also send signals. For example, if we want the next leaked signals to become larger amplitude, we will let the GPIO2 transmit on symbol, which will make the resistor B connect into the resistor. Since the resistor B is parallel with resistor A, the overall resistance will be decreased, and then the leaked signal's amplitude will be increased, and we can denote such symbol or such signal as 0, 1. Then if we want to include more amplitudes of leaked signals, we can using other GPIOs to include more different values resistors into the circuit, as shown in the figure. Now, we can already encode the information in the transmitter signals at transmitter side. However, the received signal is not the same as we expected. Due to the resonance effect, some of them will be increased. And if we directly decoding the signals based on the amplitude, we will incorrectly decode the signals as shown. The right one should be the 0, 1, but due to resonance effect, the amplitude have been increased to the largest amplitude, and we decode it as 1, 1. This is wrong. So to address the mismatched amplitude issues, we propose to encode the relative amplitude of leaked signals in the preamble part. Then, when the receiver receives signals in the data trunk, it will compare the signals in the data trunk with the signals in the preamble part, and we use the dynamic time wrapping to further increase accuracy. Then once after the dynamic time wrapping, it will show us it belongs to the 0, 1 signals. And then we will complete the same procedure until we decode all the signals correctly. Then let me show some information details of our systems. The transmitter circuits utilize the commercial LED as front end and FPGA-RTA7 as a signal source. And it also consists of different values, resistors, and MOSFETs. For the receiver coil is made by us using a copper wire and ferro core. The size of the receiver coil is about 2.54 centimeters diameter. And we also use the linear ADC to sample data and the CPLD to collect data and transmit them into the laptop for further processing. Then I'll give some basic evaluation results for our system. This is the initial setup for our experiments. The left side is transmitter and the right side is the receiver. The distance between the transceiver is set about 2 meters as default. We choose the bit error rate, BER, as a main evaluation metric for our system. And we first show the bit error rate with different distances under the different modulation levels, as shown at right side, the 4 SSK and 2 SSK. We can know that with more modulation levels, the communication range will decrease. The reason is that we need more signal to noise ratio to differentiate more kinds of leaked signals for decoding. But basically, RadioInLight system can achieve a communication range of 5 meters with 2 SSK and 2.5 meters with 4 SSK. Then another important design aspect of our system is that we could use the leaked signal for communication, but we cannot influence the original VLC channel. So we first test influence on the VLC channel of our system. First, we connecting different resistors between the MOSFET and signal source, and we can see that it's only slightly influence the VLC patterns. Then we also get the average light intensity with and without our proposed SSK modulation, and find that there is not too much difference. So we can safely claim that our system RadioInLight has little impact on the VLC channel. Finally, we will show the system data rate. We show the maximum data rate the system can achieve with bit error rate below than 0.01. And we can see that RadioInLight system can almost triple the data rate of VLC systems at 2 meters, and it can still increase 75% data rate at 5 meters. Besides, we also conduct experiment to see whether the VLC on frequency will have influence on our performance. And the result shows that there is not too much influence on the performance. So let's briefly conclude our work. First, the RadioInLight system exploited the RF leakage to increase the VLC data rate. Second, we propose a slope shift keying scheme to modulate RF leakage. Third, we designed a protocol to utilize the RF leakage for robust communication. And finally, through the comprehensive experience, we show that the RadioInLight system can double the data rate of VLC systems by using only the leaked signals. That's all. Thank you for listening.